My name is Nicole Rangel, and this is Project 4 for Dr. Osbe. I'll be doing part 1 of Project 4, the Fluent 2D flow simulator over a stationary cylinder with a diameter of 1, going over it through 3 different types of flows: inviscid, laminar, and turbulent. Alright, so first we're going to open a new fluid flow. We're going to click on geometry. Since it's 2D, make sure we change this to 2D. We're going to open new design modeler geometry. Alright, we're going to click on Z for X and Y plane. We're going to start the sketch first by drawing the circle, which will be our cylinder. It was to be one meter of diameter, so we can measure that to be 1, and then we can draw a rectangle, 2-point rectangle around it for test chamber. And then we are gonna first, let's constrain it so it's symmetrical along the horizontal axis. So now top and bottom are right in the middle, and we're going to dimension those to be horizontal to be 51, not 50, horizontal to be 50, vertical to be 21, and then the length from the left side to the center of the circle is going to be 10. These dimensions is just what worked best for the project specifically, with the laminar and turbulent cases that we used. So after that, we're going to go to concept, surface from sketches. We're going to press sketch 1, apply, and generate. This is our geometry. As you can see, it's hollow cylinder right in the middle. This is going to be the flow, and we can move on to the meshing. Now let's open up meshing. Might take a little bit to load. Perfect. Okay, so for the meshing, first we can let's name all of these first. We're gonna select the edge, press N. We can identify this as the inlet. Select the top, hold Control, select the bottom edge, press N. These are the walls. Select the outlet edge. Select the cylinder edge, press N. We can name that as cylinder. And then the face, which is going to be the fluid, we can name that as fluid. Or flow, not fluid. We can name that as flow. Perfect. Now that we have all the name sections, we can get to the mesh. First, let's do method. The method that we chose to use was triangle method. So we go here, select triangle. The body selected, which is the face, and then we're going to insert sizing. And for the sizing, we're going to do edge sizing. So we're going to press edge up there, select this, click apply, suppressed. No, the only thing here is that we're going to change type to number of divisions. Perfect. And we found that 200 number of divisions worked well with our mesh. So we're gonna do that. Curvature, no. Change soft to hard. Perfect. Let's go back to our mesh and change the element size to 0.5. And then lastly, we'll do inflation. Perfect. Here we're gonna select the face. And then we're going to select the edge here for the boundary. Change smooth transition to first layer thickness. We're going to do 0.0025 for the first layer height. Maximum layers, we're going to do 65 and keep the growth rate the same. These numbers are just the ones that worked best after trial and error. After that, we can press generate. This might take a little. Perfect. Now that it's ready, we can go back to the, well, we can take a look at it, at the meshing. Here we can look inside, see how this works here. This is the cylinder. This is the boundary. We found that the triangle method was easier to use in terms of showing the laminar and turbulent flow in the other sections. So from here we can go back to the workbench. We can update the mesh. Perfect. Open setup. We're going to do double processor, and solver processes are going to be 4 instead of 1. Alright, that's opening up. We can perfect. So first we're going to do the inviscid fluid flow over the cylinder. So we're going to go to models, select viscous, select inviscid flow. Perfect. We can close that. Then we're going to go to materials, select fluid, select air. We're going to change the air density to just 1. Change and create. Close. We're going to go to walls, boundary conditions, walls. This is going to change the type to symmetry, and the inlet, as described on the project, is going to be 5 miles per second for inviscid flow. Click apply, close. After that, we can close that. We're going to go to reference values. we're going to do from velocity inlet. Perfect. So it changes the values we just inputted and make sure that those values are being calculated, not the default values that was already in there. After that, we go to methods. For inviscid flow, it was simple and pressure was presto. Perfect. And then we can go to monitors, residuals, just for more precise calculations throughout. This is e to the -6. We're going to press OK just to make sure. Yep, e to the -6. Close monitors, we're going to open run calculation. Number of iterations, we can do 300. We're going to right click, initialize, and calculate. Inviscid flow shouldn't take too long doing the calculations. For laminar and turbulent flow, that was a little more time consuming than inviscid, but this one shouldn't be too bad. Yeah, it's going pretty fast. Alright, calculation is complete. Okay, so the first thing, let's go to the graphics, contours, save and display. This is the pressure contour for inviscid flow over the cylinder. And then we can look at our velocity magnitude, save and display. Perfect. And then here we can close. So from the velocity magnitude contour, we can go to path lines. We're going to change color by velocity, and it'll automatically change to velocity magnitude. We're going to keep that. Steps will be 3,000. Just so it shows like the whole test section. Surfaces will be inlet, displaying the velocity going through the test section over the cylinder. So we're gonna press save and display, close, and here we can take a closer look at the streamlines over the cylinder. You can see that it's uniform, goes through as expected for inviscid flow. Here we can zoom out. We can go to scene, where we can project the velocity contour over the streamlines, make it look more easier, nicer to see. Save and display. Here you can see the whole cylinder surface and the flow going over it. This is just easier to see the flows going through. We can alter the transparency to see how well it looks over. It's just really nice to the eye, and this is what we put in our report. We can screenshot it and do as fit. So for the velocity distribution, we go to the plots, XY plots. Here we can go to velocity magnitude, cylinder. We chose to compare and put all the plots together in Excel. So here you just put write to file, put it in Excel, put in a graph, all with the other flows. But since I'm just showing for the video here, we can just Save, plot, and display. This is for inviscid flow over a cylinder. That's what it should look like. And for the drag coefficients, we can go to ports. We're going to go to forces. We're going to click cylinder, click print, and this right here will be the drag coefficient. Save that, put it in your report, and this is where we're going to compare it with the experimental values that we find online. So this is for inviscid flow or laminar flow. We can go to general. We're going to change steady to transient. Models, change inviscid to laminar. Press OK. And materials, we're going to select fluid, air. Here is where we were playing around a little bit. We used the Reynolds number of 100 for laminar flow, and that came out to be air density was 1, and the viscosity was 0.8. Change and create, close. Let me just delete this right here. Okay. Let's make sure that went through. 1, and viscosity is 0.8. Perfect. Close. Boundaries, symmetries should be the walls. Perfect. Inlet was, instead of 5, it's going to be 80. Apply. Close. Close the boundary conditions, and then we're going to go to reference value, make sure it's still capturing the inlet. Perfect. It changed. Yep, 80, viscosity 0.8, density is 1. Perfect. And then from there, we can go to methods. For laminar flow, scheme is simple, which was already there. Pressure is presto. And then the only thing else is transient formulation will be second order implicit. Perfect. So then for monitors, we can check the residuals again. We can do to the -6. That's way too much, yeah. E to the -6, perfect. Close monitors. After that, we go to calculation activities. We're going to auto save every 1 second. And then we're going to run calculation where the number of time steps will be 250. Time step size will be 0.01. Max iterations will be 50. Perfect. So now we're going to right click, initialize, and calculate. We're going to press OK with that because it's just saying that we're changing the data. We're changing from inviscid to laminar. This will take a little while, 30 to 40 minutes, I would say. So I'm just going to pause the recording and come back when it is completed. Alright, so now that it's almost done, calculation is complete. We're going to go to contours. We're going to delete all the contours so it doesn't interfere with the new ones we're creating for the new flow. Delete the plots as well. Perfect. And now we're going to go to contours, static pressure, save and display. Here you would just screenshot it, put it in your report, and it just gives a nice little outline of the up and down laminar flow. One of the examples that Osbe provided. Here we're going to go to velocity. We're going to see the velocity magnitude, and here you can see very clearly the up and down flow of the laminar flow. Very nice. We're going to close that. Then we're going to go to path lines to get our streamlines. We're going to change that to velocity, and steps will also be 3000. Select inlet for the velocity, save and display. Perfect. And this is just the path lines, but we can go ahead to scene, delete the old scene, and we're going to create a new scene just to overlay the contours and path lines together so it looks nicer when displaying. So here you would just go, take a screenshot of it, put in your report, and to zoom in a little, we can see the up and down streamlines with the velocity, magnitude, contour, and path lines. This just turned out to be a really nice flow. So now we're going to go to the velocity distribution, select cylinder. Here we would write to file, again, put in your Excel, create your own graph, write, save, and display, and so the velocity distribution over the surface of the cylinder is going to be 0 because it's a no slip boundary condition. So the velocity on the walls will be 0 everywhere on the surface because this is a laminar with vortex shedding. To get drag coefficients, we're going to go to reports, forces, select the cylinder, press print, and here under total is the drag coefficient for this laminar flow. Save that, put in your report. We're going to use that to compare with experimental values. And lastly, for turbulent flow, we're going to go to general. It's already on there. It's already transient. Models, we're going to go to viscous and change it to K omega. Select. And then we're going to go to our fluid properties, air. Density will be 1, and then viscosity will be 0, 0, 1. 3 zeros. This is with a Reynolds number of 800,000. We thought that worked best with our geometry and our meshing. So after that's done, we can go to boundary. Symmetries are still walls. Inlet velocity is going to be 80. We're going to remain the same. Reference values, let's check those are still computing from the inlet. Yes. And then the method is where we're going to change. We're going to do scheme to coupled. And then second order pressure along with second order implicit. Perfect, that stays the same. And then we're gonna go to monitors, check the residuals again. That's fine. Press OK. Check the calculation activities. That should be 1 second. Perfect. Check the run calculation. 250, 0.1, and 50 max iterations. And then we're going to right click on run calculation, initialize and calculate. All right. So now that's a new flow generating. This is for the turbulent flow with a Reynolds number of 800,000. The calculation here took about a little over an hour, just because we wanted to get more precise numbers to do the comparisons and graphing. Again, as what I did with my last calculation, I'm going to stop the video and start it again when it's closer to finishing the calculation time, because this one takes a little while. So I'll be back when it's almost done. Alright, so now here the calculation is at 98%, 4 time steps remaining. It's been a little over an hour, so I just wanted to capture those last time steps in the video, making sure calculations are complete. Alright, one more time step remaining. Perfect. Alright, that was for the turbulent flow. We can press OK. And we're just going to run the same things again. Contour, pressure. This is the pressure contour. And we can check the velocity contour as well. And that's a perfect turbulent flow. Again, the Reynolds number was 800,000. So this is what it would look like. Save and display. Perfect. We're going to close. Let's get the streamlines of the velocity. Change this to 3000. Inlet, save and display. That is a perfect flow over the cylinder. We're going to close, and then we're going to go to scene, and we're going to overlay the velocity contour and the path lines just so it looks a little easier, a little nicer as well. Alright, so then we're going to just screenshot this, put it in your report. If you zoom in, you can see the lines going perfectly according to the turbulent flow. And then for the last part, the velocity distribution over the cylinder, we can go to XY plots, select velocity, select cylinder, write to file, put that in your Excel, create the graphs and everything for each of the inviscid, laminar and turbulent flow, compare that into one graph. Write to file, click close, and then we're going to go to forces, reports, forces, select the cylinder, print, and right here under total is the drag coefficients, where we're going to put in our report and compare it to all the cases, all the 3 cases that we did for this project. After all of that is done and created all of your graphs and everything, this is just a sketch estimate of how your graphs should look like. This is the velocity distribution over the cylinder and pressure coefficients over the cylinder surface. So yeah, and after that, I believe that is all we need for part 1 of project 4. Thanks.